Welcome to Unreal Science. Today we are dive into TRAPPIST, the mysterious system of 7 Earth-like worlds that may hide oceans and maybe life itself.
Imagine a world the size of Earth, circling a dim, cool star just 40 light years away. We can't see its mountains or oceans, if it has any, but for the first time, astronomers may be picking up the faintest whiff of something far more telling: air. Today's story is about TRAPPIST-1e, one of 7 Earth-sized planets packed into a compact system around an ultra-cool red dwarf. It sits in the star's temperate zone, where temperatures could in principle allow liquid water on a rocky surface. And new observations suggest 2 big things. First, TRAPPIST-1e does not seem to have a puffy, primordial atmosphere full of hydrogen. Second, there are hints, careful, tentative hints, of a denser secondary atmosphere, the kind that forms later from volcanoes, impacts, and chemistry. Let's unpack that. Planets can start life with a primary atmosphere, mostly hydrogen and helium, captured from the original gas cloud that birthed the star. Those atmospheres are voluminous and dramatic in a telescope spectrum. Hydrogen leaves big, obvious fingerprints when starlight filters through it. A secondary atmosphere is different. It's rebuilt after the violent early days, often from volcanic outgassing or from ices delivered by comets and asteroids. It's made of heavier molecules: carbon dioxide, nitrogen, water vapor. Compared to hydrogen, these gases produce subtler signals. They're harder to see, but for habitability, they're far more interesting. So what happened at TRAPPIST-1a? Astronomers used the James Webb Space Telescope to watch the planet transit, pass in front of its star, and in some cases, to watch it slip behind the star as well. During a transit, a tiny fraction of starlight filters through whatever atmosphere the planet has, imprinting spectral features we can read. If TRAPPIST-1e had kept a big hydrogen envelope, we'd expect bold, unmistakable features. Those just aren't there. Instead, the data show either a much thinner atmosphere or one made of heavier molecules whose signatures are muted and subtle. Several hydrogen-rich scenarios are effectively ruled out. What about those hints of a secondary atmosphere? Here's where caution is key. The spectra and thermal measurements are consistent with a compact, non-hydrogen atmosphere, something CO2-rich like Venus, or nitrogen-dominated like Earth with a dash of CO2. They're also consistent with an atmosphere that's relatively thin by volume, but composed of heavier gases. In other words, not a big fluffy hydrogen blanket, more of a tight, heavyweight coat. That's exactly the kind of atmosphere we hope to study on rocky worlds. Why does this matter? Because TRAPPIST-1's star is small, cool, and active. It flares. For years, the big question has been whether its planets could hold on to any air at all. Hydrogen is easy to strip away, but if TRAPPIST-1e shows signs of a secondary atmosphere, that implies resilience, ongoing outgassing from its interior, shielding processes, or both. It narrows the menu of climate possibilities. With a secondary atmosphere, surface pressure and temperature could land in a range where liquid water is plausible. Not guaranteed, not proven, but plausible. And scientifically, it's a milestone. We're beginning to constrain the actual air of an Earth-sized world in a nearby system. Of course, space is messy. Red dwarfs like TRAPPIST-1 are speckled with star spots and prone to flares, which can mimic or obscure planetary signals. Clouds and hazes on the planet can flatten spectral features. Different atmospheric compositions can look deceptively alike at first. The current result is best read as hydrogen-rich atmospheres are out. Several flavors of secondary atmosphere remain on the table, and some measurements show weak signatures consistent with those heavier gases. It's progress by elimination, and it's exactly how this kind of detective work goes. What might that atmosphere be made of? Three broad possibilities stand out. CO2 dominated, like Venus. That would trap heat efficiently. Whether it yields a hellish greenhouse or a gentle blanket depends on pressure, clouds, and circulation. N2 dominated, like Earth, with a minority of CO2 and maybe traces of water vapor. Harder to detect, but hospitable in the right amounts. A very thin, perhaps oxygen-bearing atmosphere produced by the slow loss of water or by surface chemistry, something between bare rock and breathable air. Each option paints a different climate. A thick CO2 atmosphere might redistribute heat well on a tidally locked world, softening the day-night extremes. A thinner air could preserve a stark contrast, scorching daylight, frigid night. And if there are clouds, they can both hide spectral clues and control surface temperatures. What's next? More time with Webb. Repeated transits at multiple wavelengths to firm up those faint features. Thermal phase curves, watching how the planet's heat changes as it orbits, to reveal how efficiently the atmosphere moves energy from day to night. Secondary eclipses, to isolate the planet's own glow. All of that can differentiate a dense CO2 shroud from a thinner, nitrogen-rich mix, or from a nearly airless rock. At the same time, monitoring the star's activity helps us avoid being fooled by stellar freckles and flares. If these hints are confirmed, TRAPPIST-1e becomes a benchmark for rocky exoplanet atmospheres, a nearby Earth-sized world with air that isn't primordial. That would sharpen our climate models, guide target selection for future telescopes, and yes, raise the odds that we'll find places where liquid water can persist. Not proof of life, but a big step toward environments where life, at least as we know it, could take hold. For now, think of it as catching the scent of a world's weather from 40 light years away. The aroma isn't strong yet, but it's there, and with each new observation, we're learning how to breathe in the details.